Welcome to Thermo Fisher Scientific. I am Luigi, and today we are sitting in Eindhoven in the headquarters of the Phenom development. Today we're going to have a look at how energy dispersive spectroscopy works on a Phenom desktop electron microscope. In industrial manufacturing, a typical way to measure the contamination of a sample is by counting the type of contaminants that you have in your material. EDS allows you not just to count them, but also to get their chemical composition to understand where they come from. With the live EDS functionality, we can click on the particle, and in a few seconds we will see on screen what is the chemical composition of the contaminants that we're analyzing. The technique is extremely fast, and it gives us very accurate information about the material that we're analyzing. And we don't need to adjust any additional parameter because the design of the Phenom is completely embedded in the quantification software, so the microscope will make sure to adjust all the parameters for you. But what is happening inside the sample, and where is the signal we're analyzing coming from? Let's have a look at it. When one of the electrons from the primary beam enters the electron cloud of one of the atoms making the material we're analyzing, there is a fair chance that it excites it enough that one of the electrons of the atom itself are ejected. If this happens, an X-ray is generated, which has a very characteristic energy that can be associated with the atom that generated it. By measuring the number of these X-rays and their energy, we can not just determine which elements are in the material, but also their ratio. As the signal is acquired by the detector, the software takes care of creating a spectrum, which is a distribution of the X-ray based on their energy content. So if I now start a line scan analysis across the sample, I instruct the microscope to perform a series of analyses, one after the other, that creates a line and allows us to study the distribution profile of chemical composition of different elements inside our sample. In this case, we're looking at an inclusion in a steel sample. And you can see the different chemical profile building up and being displayed on screen. As the analysis goes on, more and more counts accumulate in the spectrum, which makes over time our analysis more accurate as the beam keeps scanning the surface and generates more X-rays. Not every sample is as easy to quantify. Some of them, in fact, come with additional challenges. One of these examples is lead sulfide, which is a typical example of challenging quantification for EDS. The reason behind this difficulty is because the peak for lead and sulfur in the spectrum generated with EDS tend to overlap due to the very high similarity of their characteristic energy emission. Some of the elements have emission energy that are extremely comparable, to the point that modern instruments are not capable of distinguishing them. The result, when these elements are both in the same material, is that we will have a peak which is the sum of the two peaks from the individual element. So it will be taller, and we will not be able to see the individual contribution of the two elements. This means that complex mathematical models have to be used to be able to separate these elements, or we can recur to the use of a higher acceleration voltage. Being able to properly separate these two elements is particularly important for some applications, and one of them is forensic. Lead, in fact, is one of the main components of gunshot residue, and it's really important not to confuse it with sulfur when doing EDS analysis on gunshot residue. The quantification mechanism in the Phenom is based on forward modeling. It works by analyzing which elements are present in the spectrum and providing a first quantification. Then a synthetic spectrum generator creates a spectrum based on that composition and matches it with the one that was measured during the analysis. By iterating and using different composition, different spectra are generated and progressively compared with the measured spectra until we get the perfect match. And that results in the quantification. And this is a good example of how EDS can give you very accurate information, no matter what's the composition of the sample. In this example, in fact, you see how the quantification is extremely close to the stoichiometric ratio of 1:1, which is expected in lead sulfide. The quantification technique that we use in Phenom is extremely fast. This allows us to generate EDS map in a matter of a few seconds. The problem with the peak overlapping doesn't only impact spot analysis, but it becomes much more complicated when it impacts an EDS map. In this example, we're looking at silicon, tantalum, and hafnium in a high temperature resistance alloy. And all these elements have peaks that overlap both at low energy and high energy. The EDS quantification algorithm that's embedded in the Phenom software can take care of that and provide a quantitative EDS map in a matter of a few seconds. And we're now just 2 clicks away from saving all the information that we have and automatically generate a report which will contain all the information that we viewed in our project. Thank you for making it this far. If I made you curious today with what you saw in our software, please feel free to go to our website, thermofisher.com, and arrange a demo with me or one of my colleagues. We will all be very happy to show you all the features that we have in our software.